Hi there. Today we are going to look into AR tracking and 3D reconstruction assignment. This project covers mid to low level implementation details of the code, so let's have a look. Let's start with AR marker tracking first. For AR tracking, we need to compute two matrices, the camera intrinsic matrix and the extrinsic matrix. We start by calibrating our webcam using the calibration checkerboard to compute the webcam's intrinsic matrix and distortion. Next, we will capture images from our webcam while holding AR markers. In each frame, we compute the homography that transforms the marker image into the webcam's image using OpenCV's find homography function. The function gives us the rotation and translation matrix that make up the extrinsic matrix. Now that we have both the intrinsic and the extrinsic matrix, we can project a 3D point on a 2D image canvas using the projection equation. In this example, we render a cube wireframe over our AR marker using project points function. In the projects point function, we simply multiply our 3D point with the extrinsic and intrinsic matrix, then scale the result to get the projected points on a 2D plane. In the second part of this assignment, our aim is to create a 3D reconstruction of images that we take from our phone. We capture multiple photos of the same scene from different camera angles. In my scene, I have three main objects. Lying at the bottom, we have the AR marker, which will be used later to calculate the rotation and translation matrix. Secondly, we have a poster of Yasna Colin in search of the lost city, Urithiru. Notice that the poster is in the YZ plane and is slightly curved. We note this detail as we wish our 3D reconstruction to capture this curve in the poster. Finally, on the left, we have a simple whiteboard marker. We follow the same procedure as in the previous case to calculate the intrinsic matrix of our mobile phone's camera, and then we take multiple images of our scene to compute the rotational and translation matrices of each of our images with respect to the AR marker. After that, we pick one of those images as a reference image to compute the relative rotations and translations of other images with respect to the reference image. Once we have these matrices, we can calculate the fundamental matrix between all pairs of images. Next, we move on to computing key points and descriptor using BRISC algorithm and use brute force matching to find matches between the pairs of reference image and other images. Finally, we use the fundamental matrix to filter out matches that do not satisfy epipolar constraint. For each pair of images, we store all the points that satisfy the epipolar constraint into a data structure called feature tracks. This data structure keeps track of all the points that consistently get matched in all the image pairs. Let's call these points stable points. We will now use these stable points and the relative rotations and translations to calculate depth of each of these points and create a 3D reconstruction. Let's have a look at the result. Here we do observe 3 point clouds. The one at the front is a curved point cloud which corresponds to the poster we saw earlier. On its left, we have a small collection of point clouds that correspond to the whiteboard marker. And at the bottom we see a point cloud that corresponds to the flat AR marker which we set. The point cloud generated by another pair of images also looks similar. We have a curved cluster of points that corresponds to the poster, a small marker point cloud at the left, and a flat AR marker point cloud at the bottom. This confirms that our 3D results are correct, and with this I conclude the video.